Good afternoon, everybody. I thought today we would have a more formal review rather than just giving you an old midterm and then answering it. However, doing an old midterm and answering it as if you were taking the exam is a great way to know what you need to work on so that you don't over concentrate on any one area. Let's say if you already know it, you just need a quick review rather than, come to grips with something. Now, how the exam will be done the same way, where there'll be an upload region and a MyOpenMath, except in this case, MyOpenMath will just deliver the exam. There is really no way with my skill set and time I have available that I can automate, have a test that automatically grades it. All right. And so actually, if you want to see what it would look like, you can come into MOM and see the final exam practice. Let's see. Yeah, it's a question at a time. So these are actually, the first three questions would be from midterm 1 on the final. But then looking at question 4, that would be actually like a midterm 2 question. And yeah, say, draw the schematic of a circuit with DF2 only to do this transfer function. Now, sure, you can draw on it, but there is no way that I can automatically grade that. And so you just print out your exam, and I'll probably make sure what I need to do is have it, I think if I go to skip around, you can print out your exam and start working on it, even if your internet goes south. Okay. We have a mass spring damper, so write a transfer function. That I guess I could make that automatically gradable, right? At least what the transfer function was. But again, you have to draw the RLC circuit, which, yeah, that's just beyond my thing to automatically grade. Yeah. So I know that's what the students prefer. But when I have so many questions, having it the midterm 1 the way it did, it in some ways worked pretty well. But I can't, like let's go to multiple choice, right? That's not engineering, is multiple choice. Yeah. We got enough going on without having extra freakouts. Now, this particular question here, yeah, it is actually automatically gradable, but was more like a warm-up question, okay? Just make 3 different versions. Yeah. Now, yeah, I mean, I can make a lot of versions. Are they all equivalently difficult or easy? That's the tricky part. Then here, number 7, we're talking about controls, right? Again, I can make some kind of multiple choice thing, but again, life isn't, well, I guess sometimes life is multiple choice. You can choose one thing or the other, and then history will grade you. And then the rest of these are actually the final part after the exam. Just like today. How many questions will there be? There will be 5 questions. If you really want to see what the flavor of things are, I have sample midterms in Canvas. This one is from spring, which I guess I had given the midterm before we locked down. So that's why I don't have a my open math version, right? But it's a question, there'll be a question, something to do with DF2, right? Something to do with mass spring damper, some kind of gain bandwidth type question, a control question, and then a Fourier expansion type question. All right, Matthew, thank you for asking that question. So for drawing circuits on MOM, no, do not draw a circuit on MOM. In fact, what I'm going to do is turn off the draw capability so that you will not, and try to make the question very clear. Write this out on a PDF, okay? Just everything on that PDF, and that will be the only thing that I'm grading. Yeah. I guess when I was trying to draw here, right? So this is a third order, right? So all right, here's my resistor, here's a capacitor. I can't even do it. Okay, well, you see the sign of PDF too. Yeah, with the PDF, if it comes in on time, no problem, right? But if you've had internet connection problems, right, you need to use Adobe Scan so that it'll timestamp it, because as long as you have a cell phone connection, Adobe Scan will give the right date. But even if you can't do that, just turn it in and email me right away, even if the internet is down, because when the email is sent, it'll show that you tried, okay? But, and I'll leave it at that, okay? I'm not forcing the issue. That caused chaos when all I wanted to do is make your guys' life easier, right? Because if everybody had their document digitally signed, I wouldn't have to put a close date in Canvas, because you turn it in, no matter, as long as the document was created on time, 5 minutes late, even an hour late, you can't fake that date. It would just, I thought, would reduce the stress level. That didn't work. Yep. Again, in Zoom, just to see you, just to have a shared experience. But not really as a plagiarism detection prevention method, okay? Just so we feel that we're all in it together. Really, the only difference is you will not be entering any answers into my open math, even though there's this one question that you could. And if I did ask this question, I wouldn't be bothering checking the answers here, because that would just cause too much chaos. In fact, if I were to ask this question, I probably would take away the answer boxes so that you would know. Yeah. Yeah, Rudy, just this time it'll be skip around, and you could print no problem. It won't do that on you, okay? And even if it did give you zeros on everything and you did the PDF, then I would just fix it, okay? Now, is there going to be a practice test? Not really. The practice exams would be the old exam solutions in Canvas. Okay. And what I was going to do, I see your question, Javier, about a notch DF2. I was going to do other problems, and we can try that one at the end. All right. All righty. So let's, so this is the review before anybody asks. No, these notes aren't online yet. Okay. But they're really just a guideline for the conversation. It doesn't really have any answers. So again, well, maybe I'll start here. So for the DF2 problem, you get a transfer function, right? And then you just draw the schematic of a DF2 based circuit that implements that function. And you assume, oops, I'm recording. I see the little dot, but thank you for reminding me. We all got to help each other out, except on the exam, only moral support, okay? Not immoral support. So we assume ideal op amps, all right? You do not need to give me the R and the C values, all right? And the circuit could be second, third, or fourth order. But then as like a kind of a quick review, a second order can have high, low, band, and notch. But a third order can only have high and low. Because if you look at the notch and the band, right, you got to have an even amount of poles so that the filter slopes are evenly going up and going down. And fourth order, right, since that's fourth is, you get an integer when you divide by 2, you can do all the filters. All right. Now, as I was thinking about things, do high pass filters ever need an inverting stage to have a non-inverting output? What do you guys think about that? So I'm going to go Yoda on you, Marielle, and say you can't have a question mark. So either do or do not. So you guys are all like tentative. No, I don't know. Right. So, right. Now I'm getting more forceful answers. Okay. So yeah. No, right. And it's really that low pass. If there's an odd number, it's got to be inverted. If it's an even number, not. And then the nodes in between, it all depends. All right. But let's. So I'll just do a second order notch, right? H of S squared plus B2, S squared plus A1 S plus A2. Okay. Second order, that means I have to have 2 integrators. It's not going to work without a summer. And actually, the order in which I'm doing this, I think is a really good order to do it, because it just seems I make less mistakes. All right. Now here, this is going to give me a minus A1. I want to keep it minus. All right. So RA1. And I'm just going to shove that in there. Minus inverter times minus integrator times minus integrator is plus integrator squared. I want to invert that because it's all negative feedback. And I have two inputs here, one input. I need to balance it with a dummy. Now, this would be great, but if you can kind of get this right out, almost out of the book or any solution, what is each node, right? So this is high pass node, and this is the low pass node. Can you use LT Spice? I'm thinking. Oh, Miguel, yep, that's Miguel, right. I'm about to talk about the summer, okay? And now, yeah, Javier, this is more like a quick, here's how to do it. You got to go back, and this is even in the lab manual, what this is, but you have to kind of go and derive it. Yeah, midterm, open book, open note, open internet, not open neighbor, not open human-like intelligence, okay? And I'll just say it. I can't even spell it. I don't know. You could put your hand, let's just say the AI on Facebook has wildly mischaracterized my belief system. So use AI at your own risk, okay? Chegg, really be careful of that. I really got to tell you, okay? Many times there's a lot of wrong answers out there, okay? But the thing is I use LT Spice to check my work. There's no reason you can't do that, right? Now, if you just, let's say I ask you to do a Bodhi plot and you just print out Python Bodhi plot. Well, that's not going to fly, right? It's a great way to check your answer, but it doesn't show me your thought process, okay? But all those tools that I'm showing you in the lab manual, it's really how to check your work and how to verify things in design. And I use it to make the solutions, right? Just to make sure I haven't messed it up. Anyway, so I just label these nodes, but I haven't really said that it's an output node or not. So as many of you said, we need the B summer. So I just draw in the important parts first. And so this is now out. So having out labeled, super important. Anyway, we add for second order, right? Fourth order doesn't work like this, but for second order, right? You add in the high and you add in the low. The high is, like you guys have said, it's never inverted. Of course, unless the input is inverted, right? So B's are not inverted, all right? Where the B's are always added, right? The A's, while they're added in the transfer function, it's the way the negative feedback works. And so this node here is non-inverting. And so we want to keep it that way. And we can call that our I don't know, RB0 and RB12. I have 1, 2 inputs. I would have 2 dummies. Now, of course, these are in parallel and you can do 1. Why do I put 2 dummies? So you can maybe see my thought process. All right. But this is for the notch filter. All right. And I will say what it is. All right. Implement this high pass, implement this low pass, notch, band, and then I give you a thing. You may answer the question after this. Are you saying we can't turn this? I need to see your thought process, Marielle. Yeah, so hand drawn is really the way to go. But you can do both. Okay. So that's that. Now, yeah, there's the high pass version, there's the low pass, there's the band pass. We can do it for 3rd order, we can do it for 4th order. Right. It's, oh, please don't turn the paper in sideways. Oh, that drives me crazy. Listen, I do have 108 exams to grade. Please, just like the homework, all straight. Okay. That lands it. Okay. Just please. Now, of course, if you're making a mistake or you're having a panic attack, I will grade it. But okay. So that's a sample, right? Here's all the things, though, that it could be. Now, I was thinking about DF2. Landscape is the devil. Anyway, here's a transfer function for a low pass 3rd order filter. Here is the Bode plot. I mean, not the Bode plot. Here is a schematic, right? So what would happen, right, if A3 were 0? Oops. So this is not here. Okay, so in fact, no, with that S cubed in this structure, no, there's still 3 integrators, right? But notice I can then do this. And it goes integrator on me. How could that happen? Well, easily. You're tired and you forget to wire it up. Now, this is a 3rd order filter, so it's inverting. So you should notice I have minus VLP here just to keep myself sane, right? And you see that there's some delay and then it goes up, 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 and then it hits the rail, right? So that is, the input is a step. We're getting some kind of integration, and look at it. We have some circuit that is then fed into an inverting integrator, right? Now, the trick is and this is a trick question, and so I'm just going to tell you, but notice the high pass, it's underdamped, but it's still acting like a high pass step response, right? It detects the edge and then it oscillates. Well, what's going on is that it's not fed back in, right? And so this might as well not even exist. And it's actually, by taking that out, you've actually made it into a second order circuit, right? What if A2 was missing? I don't know, let's see. Oh, we got an oscillator. That means we have to have complex poles, right? And that's an oscillator too. All right. So the thing is if you're seeing this kind of thing, right, is this system in control? No, it's oscillating. Why would it be oscillating? Well, somehow having this one or this one set to 0, right? If you use the, you can use Python and the root function to find the roots, you'll see that it is, it's got purely complex roots in it somewhere. It can still have real roots too, but a pair of complex roots will cause it to oscillate. All right. And so we saw what happened when it was an integrator. Now, what if one of the constants were negative? All right, let's see. So I'm going to take A1 and kind of draw it in a very annoying fashion here. Now I have 1, 2 inputs. Here I have 1, 2, 3, 4. So let's see, now I have 1, 2, 1, 2. All right, so it should be balanced. But A1 is now, rather than a positive number, it's negative. All right, so it's giving me an oscillator. Although I thought it would have given me exponential increase. But this is a third order circuit, so right, what kind of questions on control could we have, right? What if his A3 is 0? What if A2 is 0? What if A1 is 0? Okay. What if one is, this is negative, that's negative, that's negative? Well, they'll all be out of control, right? The solution is to wire it up properly, right? But that's, I guess what I'm saying, here's how you can use control theory to kind of figure out what you might have accidentally done wrong with your circuit. Although sometimes you do want to make an oscillator on purpose. Oh, how do you make an oscillator? Well, I guess you could just start deleting things. Or, you know, rewrite this equation so you get complex poles. All right. Again, this one was tricky because when you got rid of A3, you just turned it into a second order thing. All right. Now I'm kind of, this is more like review and ideas. I was going to come back and maybe do a sample. All right, but I wanted to talk about gain bandwidth. All right. So sometimes, and there's a lot, I have a lot of examples, is that you have a gain bandwidth problem, and I'm asking you to come up with a sample equation, right? But sometimes I ask you to do it graphically. Doing this problem with an equation can get pretty involved. All right. But let's just, before we get involved, gain bandwidth. That is the frequency that the op amp will have where V out equals V in. All right. So if I'm to ground and V in is a value when V in equals V out, the gain is 1 or 0 dB, whatever frequency that happens. So if I'm looking at this plot here, V out is the open loop gain, right, of the transfer function of the op amp. And yeah, the pole is a lot bigger than 1, but then you start to see it. Oops. You can't see the gain bandwidth there. So the DC gain, it's 120. And yeah, you read that off of the data sheet and you can just draw a line straight out. Then if they tell you the gain bandwidth, in this case, I know that it's 10 megahertz, right? Op amps are designed so that this first slope is 20 dB per decade. So if I'm 0 dB here and I just draw a line and go up 20 dB for every decade, right? There's my asymptotic Bode plot. And I just have to keep the magnitude of my transfer function below that. But right here, where the gain is 0, right, is my gain bandwidth. But to truly see what's going on, you also need the DC gain, right? Now, yeah, you can, this is a universal op amp, and you could set what the gain, I can say I want 0.1 gain bandwidth. I come across 0 dB, oops. Right, it's right there. So with the DC gain, and you draw a line, out, and then the gain bandwidth, so you draw a line with 20 dB slope per decade from there, you get the area under this curve, right? You want to be below that. Well, let's do, I thought I had an, all right, hold on. There's a chat. Actually I show you that in 122. But really you just, right click and then click it right here and just edit it. Okay. All right, so now we're back to where we are. Now, this is an inverting integrator, and its transfer function is -1 over S, right? Based on those values. Now, to do this in a behavior voltage source, you can do 1 over S, but you have to add a very small number, otherwise you get a divide by 0 or error. And so this is check inverter, right? So let's just plot that. And so this blue line is that, not inverter, integrator, right? And the phase you can see is, oops, my bad. Integrators have a phase of -90. This is inverting, so it should be a phase of +90. All right, so here's this Bode plot of the transfer function of the op amp, and here's the integrator, the ideal thing that we want. And these look in parallel, so it looks like it's okay at high frequencies, but at low frequencies, right, an integrator, if that's 1 over S, well, when at DC, an integrator will go to infinity, right? And so look how far I had to go out, 1 nanohertz, right? So that's a very long time, okay? But see, it crosses that line. And so that's where, you know, the usable range is to the right of that. Now let's do the op amp. And you can see, yeah, it's starting to roll off. It's not working, right? And at high frequencies, it's deviating. All right. And I will have to show you a lot of math as to why it's doing this odd thing. But it is, it's a gain bandwidth issue, and gain bandwidth are caused by the feedback capacitors to keep the op amp stable when you put it with feedback. Okay. While this can be stable on its own, when you put feedback in it, it can go unstable. And that's really all I want to say about that today. All right. In 124, you see what's going on with that. All right. So that's what I might call the graphical method, right? Or what's another sample for that? Oops. Now the gain should be -1, right? Or 0 dB, and then the phase would be different. All right, let's just get rid of our check function. Where'd it go? So notice the gain is 0 dB, and it starts rolling off even before it gets to this here. So the thing is it can't really go to the line. It's somewhat below. And inverting op amps, it's hard mathematically to show that. But really, if you said, yeah, the gain is -1 and it should work until it hits that line, that's a great first approximation, right? But it works really well for non-inverting. So here, right, we should have a gain of 2. Something's not right. Okay. I had that set wrong. See, it still rolls off before, but it's very close. Okay. So if you said that it's going to stop working at wherever, let's do a 10. Gain of 10, 20 dB, right? So I just draw a line 20 dB out and say it stops working at a megahertz, right? Oh, it's rolling off before that, but that's a pretty good approximation. Okay. And then if I even do, you know, just some higher gain, right? Notice that the frequency is even reduced from there. And that would be the graphic thing. And that's right off of the homework, okay? Now, sometimes I say, please do it mathematically. Sometimes I say, do it graphically. Sometimes I say, do it both. You really, really got to follow those instructions, okay? So Marielle, there's these internal capacitors inside the op amp that are used to stabilize it, that you put there on purpose. The reason why it's unstable is that there's capacitors there that come about because of the diodes that are in the transistors. And there's a, that cause what is known as a zero on the right-hand plane, which doesn't mean you're out of control, but a zero on the right-hand plane, when you put feedback, can become a pole on the right-hand plane, and you have an instability, okay? But that is advanced. That's not going to be on the exam, I don't think. Okay, so I have a fixed surface, right? And so that is like my ground, and I have a mass, right? Which, yeah, if I were to actually connect the mass to the fixed surface, well, nothing would happen, right? So I have to draw that capacitor, but one end is related to ground because the velocity at y, right, Vy, is represented as a voltage with respect to ground, all right? So I draw that, I have a fixed surface, and I have a damper, which is a resistor, right? And then one end is tied to the mass, right? Now, if I were to draw it the other way, and then connect it like that, well, now I've connected this, both sides of the capacitor to ground, and that's not going to work. Now I have the moving platform, that is the input, and it goes through the spring. All right. Now, for the damping conditions, right, you know, I like to use impedance. And what I see is that these are in parallel with, it's a voltage division of these two impedances in parallel with this inductor. Okay. Which I don't have memorized, and I would just have to do it just like you. Okay. But this is the transfer equation, which it now doesn't want to move. Anyway, what are the damping things? Well, we have our quadratic equation, right? Minus b plus or minus b squared minus 4ac 2a, right? What's b? In this case, it's 1 over RC. When everything is in series, it's R over L, right? And then 4AC is 4 divided by LC, right? And so you basically get is 1 over RC squared. Is it greater than, equal to, or less than 4LC? Now, this system can actually be out of control, right? And how would that be? Well, what if B, this B term, not to be confused with the damping coefficient. Where 0, I'd have complex poles. How could I get B 1 over RC equal to 0? Well, if R goes to infinity, B goes to 0. So if R is going to infinity, well, what's that like? Well, that's like if you just took it out. So what if you had this damper moving back and forth and it's got the liquid in it or however it's doing it, and it totally broke and you had a piece here and a piece here and it's just flapping around, right? It would start to oscillate, right? And anybody who's had bad shocks, right? You hit a bump and you oscillate for a very long time. Now, do you oscillate forever? No, but you're effectively out of control. Yeah. I mean, yes, Nick, that is a parallel low pass circuit, right? Yeah, so Rudy, right. You think it's going to be series because it looks like it's all in series. So how can you tell, right? So let's just do a few examples. Or let's do another example, right? So this is my input velocity. Here's an L, here's an R, here's a C. And you're like, well, Vy is always across the capacitor, okay? But what if I wanted just to find, the resonant frequency? Well, I would just set this to 0, right? So then I have an inductor, I have a resistor, and I have a capacitor. They're all in parallel, and that gives you that R over L in the denominator, right? So in this case, where we had this, well, that's my input voltage. But if I short it just to see what the system is doing, you can see that the resistor, the capacitor, the inductor are all in parallel. So the denominator is still this, but the numerator isn't the same, right? And then you could have, let me just draw that more inductory. All right, what if I want to see what's going on here? Short the input. You can see all of these are in parallel. And so you get the parallel denominator, right? The only way to get the series is this or this. Because if I tie it to ground, right, all the current is the same. Tie it to ground, all the current is the same. Now, in fact, the denominator of V out will remain the same because it doesn't matter the order, right? It's the voltage division would be ZC divided by the sum of these impedances. Doesn't matter if these are out of order. So here's a transfer function, right? A standard low pass type transfer function, right? And I'm saying let A4 be 0. So we just get rid of it. Let A2 be negative. All right, so I'm just going to draw it like that. All right. So in this case, right, I have two problems, right? Missing power of S, because A4 is S to the 0, right? So I have a missing power of S, and I have a sign change, right? So I have to come up with something that allows me to change a sign and allows me to have something with a power of S. So all right. So I can look at it and say, I need something S squared so that I can make it bigger so that when I add it, I can turn that positive. And now here I just need something, right? So I need just like a constant, right? And when I multiply these two together, this is what I have to get, right? So as you do a lot of these, you can almost see the solution before you start. And why is that? Well, H of S, or excuse me, Q of S, right, is equal to H of S, 1 plus. All right, this is from the signal flow graph, right, where I have HS is my original thing, right? And if I put the input in, I have an out of control system. G of S, oops, we feed back in a negative format. And when you do that, you get this equation. And then if H of S equals a numerator divided by a denominator, and I plug that in, right, I get the original numerator, I get the original denominator because I multiplied it by 1, but then I get the original numerator times the feedback, and the denominators had canceled out. So where's the original denominator? Well, it's right here, right? That's the original. But now I get to add, right, B4 times G of S, and G of S can have more than one term, right? And so that's how I can fix it. Now that's getting a little sloppy there, so let's. Wait, how many were there? So A2 is negative. Plus nothing, right? Q of S equals H of S, 1 plus here. All right. So again, here's my H of S. Right? Remember, this is the denominator, which I multiply by 1. So that's why I've got the original denominator. Then I have whatever my G of S is, but I'm multiplying this whole denominator through, right? Here's the denominator of HS gets replicated here, but then it gets canceled here, and now I'm left with a numerator, B4. Okay? So now just looking at it, the easiest thing is to not turn everything else negative, but to make this one positive. All right. So what would make that happen, right? Let's just call it G of S1 times B4 has to equal we always have some kind of constant, right? But it's got to equal something squared, right? So really, GS1 equals K1 all right. Now, when I add this to here, right, I'm going to have S squared K1 divided by B4 minus A2. In order to make this positive, this has to be bigger than that, right? So K1 B4 has to be greater than A2. All right. Now I'm missing a constant, right? So G of S times B4, I just need some kind of constant, right? Okay. So really, G of S is K2 divided by B4. All right. Now, if everything else is positive, how do I keep that positive? That's easy. K2 greater than 0. All right. So, yeah, imagine if all of these are missing. Well, I'd have to have G of S times B4 equal to K, so that I'd have a constant. Then I'd have to have some kind of K times S to bring it here. I'd have to have some kind of K times S squared, some kind of K S cubed to bring all of these back, right? Now, of course, right, this transfer function, let's look at the numerator, right? Let's keep that denominator the same, right? I could have B naught to the fourth, right? I could have B1 here, B2, B1, And then we already talked about B4, right? I could have them added together, right? I could have a combination, but that G of S times that numerator, right, has to equal something that makes everything the same sign. Make sure all powers of S are present. All right. Now let's talk about Y's. Now let's say A3 is missing, right? And you're asked, why is it out of control? And you say, A3 is missing. It's true, that's what's making it out of control, but it doesn't really tell the whole tale, right? You could say it's missing, thus it'll cause a pole on the right-hand side, which could give me complex poles or at least one. It can give me a set of complex poles, which will cause an oscillator. It can give me at least one pole on the right-hand side, where the real part is on the right-hand side, which will give me exponential increase. Or the pole could be 0, which will give me an integrator, right? Now, the thing is they all have to be missing in this example. Like A3 being missing does not make that it can't be an integrator, right? That's an integrator, right? But the other ones aren't. So you have to be more specific as to, you can't just say it's missing, right? Or the sign is, yes, I can tell the sign is wrong, but what is that going to do, right? Now, sure, you could, there's something called NP roots, and it'll tell you what the roots are. And so here I got a pole at 0, and then a pair of complex poles at plus or minus J, right? But I guess the other thing is like that kind of it was almost a matching game, right? Where we looked at hey, it's oscillating. Can it be an integrator? No. Can it be exponential increase? No. It's got to have only complex poles. Because if you had complex poles and it was an integrator, it would just keep going up. If you had complex poles and the real part greater than 0, you would have exponential increase. And it would swamp out these oscillations. You'd never see it, okay? So just by seeing what's going on, you can kind of tell, right? Now, I haven't really gone over this, but really, usually the problem is something like this, and everybody does really well. Or I say, here's sine omega naught t sine omega naught t, right? Oops. And you have something at 0 hertz. And then you have something at 2 omega naught, right? Well, this doubles the frequency, and it also takes a sine wave like this and makes it all on one side of the axis. So that's where you get the average, right? And I'm like, all right, what if I have sine 2 omega t, right? Well, there is no DC component of that. And so I give you two functions, I give you two plots, right? And you have to choose which one, right? Then you can have let's say that's a quarter of a duty cycle, right? Well, then that first fundamental frequency, these aren't on the same axis, right? It's still the same fundamental frequency, but the average is a quarter of whatever V peak is here, right? If it was 50, then it would go up to 50%. If it was 75, it would go up to 75. But this fundamental frequency would happen at the same place. So it's like a detective game. I give you all these various things, right? Another one is like having sine omega 1t plus sine omega 2t. So there's two separate things, right? Now, of course, this has these pulses, right, have an infinite series. When it's 50%, right, it's only the B constants. So that's, you know, pretty much my thinking on exams. Now, sure, if you look at the final, right, I might say here's a Fourier, you know, here's a spectrum of a waveform, and I'm like, what kind of filter? Let's call that omega naught. I'm just making this up, 2 omega naught, 3 omega naught, right? What kind of filter would I draw to get to do the DC? Oh, I would just do something like this, right? Low pass gets DC. I want a sine wave that is omega naught. Oh, okay. Right? Band, right? That captures that, right? I want to get rid of the DC. Oh, all right, let's get rid of it. That's a high pass, right? I want to get rid of just this one thing here. I want to get rid of that. All right, well, then that's a notch. This is more final exam, okay? But that's pretty much what I have. If you guys have anything, you can just ask it now. Now remember, some of the homework is due, hard due on Sunday so I can send out the solutions, okay? For the control ones. All right.
Thank you. Have a wonderful weekend.
All right. Oh,
Is the homework due
you
on
too.
Sunday or Saturday?
Whatever it says.
Is that Saturday?
Yep.
Okay. All three of them, or just?
Whatever it says.
All right, that's fine.
Okay.
Yeah, just one.
I have to look it up. I got to
Yeah,
look it up
okay.
just like you do.
Professor,
Yeah.
I wrote a question in the chat.
Well, yeah, I'm going to post the video as soon as it's done. And the notes, like I said at the beginning, I said they're not posted yet, but I'll post them. You know, they don't have any answers, right? But it, you know.
It's
Sure.
a pretty good guide.
Yeah.
All right.
It's
Well,
just
thank
the
you.
thought process. All right. Take care.
Bye bye.
All right. Have a good day, everybody.